When the neuron is at rest, that is, when it is not sending or receiving information, there is a difference in charge between the inside and the outside of the neuron. This difference in charge, which is about -70 millivolts, is known as the resting membrane potential. In other words, at rest, the nerve cell is negative on the inside relative to the outside. A neuron at rest is similar to your cell phone at rest. It's on and ready, and it requires energy to stay ready, but no one is calling or texting you, and you are not calling or texting anyone. If conditions change, however, and you text someone or a call comes in, your ringtone begins to sound, the phone may vibrate, and the phone springs into action. A neuron springs into action in a very similar way when a message comes through. The force of diffusion moves ions down their concentration gradients from areas of high concentration to areas of low concentration. It's similar to when you put a teaspoon of sugar into a glass of iced tea. The sugar initially is concentrated at the bottom of the glass. The sugar slowly moves down its concentration gradient, or diffuses throughout the glass of iced tea, until it is evenly dispersed and every sip of tea tastes sweet. Sodium-Potassium Pump exchanges sodium for potassium ions across the cell membrane. The pump requires energy to maintain the resting potential, much like your cell phone requires battery power, even when it is not actively sending or receiving messages. Three factors help to keep a neuron at rest: diffusion, electrostatic pressure, and the sodium-potassium pump. On each side of the neuron cell membrane are ions, or charged particles, of sodium, Na+, potassium, K+, and chloride, Cl-. As you can probably guess, sodium and potassium are positively charged ions, or cations, and chloride is a negatively charged ion, or anion. There are also large organic anions, A-, which are negatively charged, located inside the neuron. The forces of diffusion and electrostatic pressure act on these ions. The large organic ions want to move down their concentration gradient out of the cell because there are more organic anions inside the neuron than outside, much like there is more sugar concentrated at the bottom of your glass of iced tea. Electrostatic pressure wants to also move the organic ions out of the neuron because they are negatively charged particles and therefore are repelled by the negative charge inside the neuron. However, the cell membrane is impermeable to these large organic ions, so they are stuck inside the neuron. As a result of their inability to cross the cell membrane, the large organic ions help maintain the negative internal charge of the neuron at rest. When the neuron is at rest, there is more potassium, K+, inside of the cell than outside. The diffusion force pushes potassium down its concentration gradient, through the membrane and out of the neuron, but electrostatic pressure pushes the positively charged potassium in because it is attracted to the negative internal environment. Therefore, the potassium level stays balanced, which helps to keep the neuron at rest. There is also more chloride, Cl-, outside of the cell than inside at rest. Diffusion pushes chloride down its concentration gradient, across the membrane, and into the cell, but electrostatic pressure pushes chloride out because it has a negative charge and is therefore repelled by the negative charge inside the resting neuron. At rest, there is more sodium, Na+, outside of the cell than inside. Sodium has a positive charge, so it is naturally attracted to the negative charge inside the cell. Therefore, both diffusion and electrostatic pressure want to push sodium into the cell. Note that unlike potassium and chloride, both electrostatic pressure and diffusion push sodium in the same direction, into the cell. As it moves down its concentration gradient and is attracted to the negative charge inside the neuron, sodium brings its positive charge with it, eventually making the neuron positive on the inside and active, not at rest. So to maintain the resting potential, sodium must be pumped out of the cell. This is where the sodium-potassium pump comes in. The sodium-potassium pump actively exchanges sodium for potassium to keep the ions balanced and to maintain the resting potential. The sodium-potassium pump requires energy to pump out sodium, just like your cell phone requires energy or battery power to quietly wait for messages to be sent or received. The action potential consists of 3 phases, each resulting from shifts in voltage or changes in charge across the cell membrane that selectively open ion channels and allow ions to flow across the cell membrane. During the first phase, voltage-dependent sodium ion channels in the cell membrane open and allow sodium to come rushing into the neuron. Sodium brings its positive charge with it, which changes the charge inside the neuron to positive. Since the inside of the neuron is becoming positive with the influx of sodium, the change in electrostatic pressure results in the opening of potassium channels, and positively charged potassium flows out of the cell. The sodium channels then close, and the peak of the action potential is reached. As the influx of sodium decreases, potassium is still leaving, resulting in a temporary hyperpolarization of the cell membrane potential. When the potassium channels close, the sodium-potassium pump begins exchanging potassium and sodium again, and the baseline potassium level is once again restored on both sides of the membrane. Once triggered, action potentials proceed down the axon to the terminal ending. Action potentials abide by all or none law. Once depolarization or an EPSP reaches threshold, an action potential will occur, and it can't be canceled. Just like sending a text from your cell phone, once you hit send, off it goes, and you can't stop the message from being delivered. Many axons are covered with an insulating substance called myelin. The myelin is wrapped tightly around the axons, and it speeds up the rate of neural communication. In other words, the action potential will travel much more quickly down a myelinated axon than a non-myelinated one. The process of traveling down a myelinated axon is called saltatory conduction. The myelin squeezes all of the sodium channels to concentrated regions between successive patches of myelin. These myelin-free areas are called nodes of Ranvier. Saltatory conduction involves propagation or jumping of the action potential down the axon from node to node of Ranvier. Following the action potential, neurotransmitters are released into the synapse. The transmitter molecules bind with specialized structures called receptors on the postsynaptic or receiving neuron's membrane. There are 2 different types of receptors on a postsynaptic membrane: ionotropic, or ion channel receptors, and metabotropic, or G-protein-coupled receptors. When a neurotransmitter binds to an ionotropic receptor, the transmitter-receptor complex generates rapid and brief changes in postsynaptic neuronal excitability. In other words, the binding of a neurotransmitter to an ionotropic receptor results in the opening of ion channels across the postsynaptic cell membrane. Depending on the type of ion channels that are opened, sodium, potassium, calcium, or chloride, for example, will begin to flow into or out of the cell, inducing either EPSPs or IPSPs in the postsynaptic neuron. The binding of transmitters to receptors, which opens membrane ion channels, is the mechanism by which the chemical message between neurons is converted to the electrical message within neurons. Metabotropic, or G-protein-coupled receptors, work indirectly to change the excitability of postsynaptic neurons, either by changing calcium ion levels inside the neuron or by activating second messengers. The activation of metabotropic receptors result in slower, longer-lasting, and more complicated postsynaptic changes. These postsynaptic changes range from the opening of ion channels to changes in internal calcium ion levels to changes in gene expression. Neurotransmitter activates the receiving neuron's receptors, the message has been sent and the transmitter is no longer needed in the synapse. In fact, if the transmitter remained in the synapse, it would repeatedly bind to the postsynaptic receptors, activate them, and keep inducing EPSPs or IPSPs. The postsynaptic potential effect, or release of neurotransmitters, is terminated in one of two ways. The first is known as a process called reuptake, where the neurotransmitter is taken back up into the sending neuron and recycled for release following another action potential. The other, called enzymatic deactivation, involves enzymes breaking down the neurotransmitter into inactive components. The components are then taken back up and recycled. The nervous system is very conservation-minded. It recycles and reuses neurotransmitters. So far, we have been talking about neural communication as if there are only two neurons involved, a sender and a receiver. However, much like your phone communication system, where you can be receiving multiple calls, texts, and emails from several friends at the same time, neurons also receive multiple inputs. Neurons integrate and summate the multiple subthreshold inputs, the EPSPs and IPSPs they receive, across time and space. If the sum of all EPSPs and IPSPs received close together in time and space exceeds threshold, then an action potential will be triggered. For example, let's say you hear a rumor that there is going to be a great party on campus next weekend, but you don't know whether you'll go or not. Going to the party would mean that you could spring into action and do something, much like an action potential. However, the rumor is like a subthreshold EPSP. It arouses your attention, but is not a big enough or beyond threshold message to actually get you to commit to going to the party. As you continue through your day, you receive multiple messages from your friends about this party. Some friends call, text, Facebook, or email to tell you that they are going and that you absolutely should come. These messages are like EPSPs, or depolarizations. Other friends contact you and tell you that the party won't be any fun and that you shouldn't waste your time. Those friends may even entice you to attend a different event at the same time as the party. These do not attend the party messages are hyperpolarizations, or IPSPs. The IPSP messages move you further away from deciding to attend the party. Ultimately, you make a decision to attend the party, that is, have an action potential or not. Your decision is based on the sum of all of the EPSP and IPSP messages you received across time and space from your friends. If the sum of all of the messages is a depolarization that exceeds threshold, you will spring into action and attend the party.